Hey, this is Math 8, Unit 7, Lesson 1. First of all, with some exponent review. So we began first of all today with four little expressions here, and it asked you which one does not belong, and wanted you to talk about that with your partners for which one doesn't belong. So if you're doing this with the class and your teacher isn't here today, then you can take a look at these four items here and have a little discussion real quick about which one doesn't belong. So you can pause there, chat about that, have a good discussion, and then let's move on to activity number 2. Now, activity number 2 is called Return of the Genie. It says, May and Andre found an old brass bottle that contained a magical genie. They freed the genie and offered them each a magical $1 coin as thanks. The magic coin turned into 2 coins on the first day. So we had 2 coins on the first day, 2 coins into 4 coins on the second day, and then 4 coins to 8 on the third day. This doubling pattern continued for 28 days. Wow, that's pretty cool. May was trying to calculate how many coins she would have, and remembered that instead of writing 1 times 2 times 2 times 2 times 2 times 2 times 2 for the number of coins in 6 days, she could just write 2 to the 6th power. Notice here that we have how many 2's? 1, 2, 3, 4, 5, 6, right? So it's important to just kind of keep that in mind. You started with 1, but the day you begin counting that you doubled it that's the first day there, okay? So it's 2 to the 6th power. The number of coins May had on the 28th day is a very, very large number. Write an expression to represent this number without computing its value. So if on 6 days, and then on the 6th day, it's 2 to the 6th power, then what we're saying is that on the 28th day, we would write down that it's 2 to the 28th power. And that's the idea there, that we're simply repeating that multiplication of times 2, that doubling, which is times 2, 28 times over the course of 28 days. Andre's coins lost their magic on the 25th day. So May has a lot more coins than he does. How many times more coins does May have than Andre? Well, let's think about Andre first of all. So Andre, his worked until the 25th day. So his went 2 to the 25th power, whereas May, hers went 2 to the 28th power, right? And so what's happening is we're multiplying here. This is 2 times 2 times 2 forever and ever and ever. So is this one, but the difference here is that I have 25 of them there, and I have an additional 3 times there. Now, I said 3 times, but what we mean by that is what? 3 of what? Well, we're going to be multiplying everything, doubling it 1 time, 2 times, oops, sorry, I was saying 3 and writing 3, 1 time, 2 times, and 3 times more. So what we're doing 3 more times is we're multiplying by 2 3 more times, right? That's the difference from 28 to 25. So how many times more coins does he have is 2 times 2 times 2. Well, 2 times 2 times 2 is actually going to be 8 times as many. So the times as a word kind of throws you off a little bit in thinking about that. But again, this is does it for 3 more instances, 3 more days. So instead of using the word time, 3 more days, and each day that happens, it's times 2 times 2 times 2. So that takes place 3 different occasions, and so we would say it's 8 times as many because 2 to the 3rd power, or 2 times 2 times 2, ends up being 8. All right, let's take a look at the next one. The next one's called a broken coin. So instead of getting greater, it tends to get less. It says after a while, Jada picks up a coin that seems different than the others. She notices the next day only half of the coin is left. On the second day, only 1/4, and on the third day, 1/8 remains. So what's happening is it is cutting in half each time. So on one day it cuts in half, then it cuts in half again, then it cuts in half again, right? It started off as a whole coin, but it just keeps continually being cut in half, or multiplied by 1/2. That's how we're going to show that it's cutting in half each time. So what fraction of the coin remains after 6 days? Well, again, if this is what day after the first day of doubling is, that's day 1, right? This is day 2, day 3, day 4, day 5, and if I was to write another one, that becomes day 6. What we're having here is we have 1/2, and this is being done how many times? 1, 2, 3, 4, 5, 6 times. I have that repeated multiplication taking place 6 times. So what fraction of the coin remains after 6 days? Well, we could write it as 1/2 to the 6th power, But I could also then solve that, because this becomes 1 over 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, and 32 times 2 is 64. So the fraction that remains is 1/64th is what remains after 6 days. What fraction of the coin remains after 28 days? Now again, it's the same idea, right? We know that we're going to be cutting it in half each time, and we're going to do that for a total of 28 days. Now that's a lot of days there, isn't it, right? So it's 1/2 28 times. And that's the same thing we did up here, right? So it's just like saying 1/2 times 1/2 times 1/2, and continue to do that 28 times. So eventually reach the point that it just makes more sense to write it as 1/2 to the 28th power, meaning we're going to repeat multiplication doing times 1/2 28 times to find out how much is going to be there after 28 days. All right, now I'm not going to get my calculator to do that. That would take a long time. So does the coin disappear completely? The answer here would be no, it does not. And the reason for that is you always have half as much. If I had a whole coin and I take away a half, then I'm left with that. It's not going away, it's just half of what it was before. If I only had this much and I take away half, well, now it's down to that. And again, this piece is going to become very, very small as you keep doing that, but you'll never run out of a piece. It just gets super, super small. Hard for me to draw, but it's always going to be there. On the "Are you ready for more?" question, it's a good question just in terms of understanding, again, how this exponent is repeated multiplication. It says Tyler has 2 parents and each of his parents has 2 parents. Draw a family tree showing Tyler, his parents, his grandparents, and his great-grandparents. So let's say, for example, that we have Tyler here, okay, and then Tyler has a parent over here, and just for the sake of this, we're going to just write down mom and dad, okay? We'll just leave it like that for now, just easy to write 2 different letters. So that becomes the parent, and then the parent has their parents. We could write M and D, and these parents have their parents, M and D. All right, that becomes Tyler's parents. Now here's Tyler's grandparents, and great-grandparents is one more level, isn't it? 1, 2, 1, 2, 1, 2, 1, 2. All right, mom, dad, mom, dad, mom, dad, mom, dad. All right, so we have multiple levels of kind of generations taking place here. This is our great-grandparents, and that's what the tree would look like there. So for our tree, for example, what we have is we have Tyler. Okay, now Tyler is the first person, right? So we know that we're going to be looking here. This is 2. Well, Tyler's the first person. Okay, Tyler's the first person, and we know that because it's splitting into 2 people, we're going to multiply it by 2, in this case here, to the 0 power. 2 to the 0 power is actually the same as 1. Okay, anything to the 0 power is 1. So on the first level we have 1. Here we have Tyler, and we have 1 set of parents there. So we're going to go 1 times 2, so the first power, which is 2 people. Good so far? Here, of course, we have 1, and we have 2, a group of 2 there, and we have another group of 2 there, so this is 2 squared, right, which is 2 squared, which is 4. That's the number of people in that row there. And here we have 1 times 2 to the 1, 2, 3, 4th power. Fourth power? Oh, we're in 3rd generation, so 3rd, sorry, don't do 4, sorry. We're on our 3rd time we're doing it, multiplying, doubling everything by 3, or by 2. And so now we have 2 times 2 times 2, so we're left with 8 people in this row. So this becomes, the part 2 here, is 3 generations back. That generation is the exponent we're talking about. 2 to the 3rd power is the great-grandparents. And that ends up with 8 people. At which generation back does Tyler have 262,144 ancestors? So the question here is 2 times what exponent is going to get you 262,144. How many times would you have to multiply 2 times 2 times 2 times 2 times 2, right, in order to get to that number is the question that they're asking. And so if you were to maybe take a calculator out and repeat that multiplication process again and again and again, what you would find is that it would take until the 18th generation to reach that number right there. All right, so that is kind of some basics of what today's lesson was about, just reviewing exponents there. And again, exponents make it easy to show repeated multiplication. And that's what we're saying here. When it's 2 to the 6th power, we're multiplying 2 by itself 6 times there. And so it's just a lot easier to write it that way rather than having to think about how would you write out 2 to the 100th power. Just doing it again and again and again, it's just a lot faster to do it that way, and so it's kind of cool. All right, pause there, and then let's work on your homework, and then we'll come back and check that together. All right, homework time. Math 8, Unit 7, Lesson 1. Write each expression using an exponent. Okay, so I'm going to say this is 1 times 7, so that's just a 7. But how many 7s do I have? 1, 2, 3, 4, 5. So this is 7 to the 5th power. For B, we have the 4/5, but we're going to have how many of them? 1, 2, 3, 4, 5. So this is 4/5 to the 5th power. The next one we have 9.3. In 9.3 we have 1, 2, 3, 4, 5, 6, 7, 8 of those. So it's 9.3 to the 8th power. And finally, the number of coins Jada will have on the 8th day if she starts with 1 coin and the number of the coins doubles every day. So again, on the first day of doubling is where she has 2 on the first day. So that'd be on the first day, she has 2, but we want to go all the way to the 8th day, so we would say 2 to the 8th. And 2 to the 8th power is the same as 2, 2, 3, 4, 5, 6, 7, 8. Multiply all that together. Again, a lot to multiply out there, isn't it? Okay, and so that's what you'd be looking at there. But we want to write it as an exponent, so we just say 2 to the 8th. That's a lot nicer and cleaner than writing all that out there. Number 2, we're going to evaluate the expressions. So this is 2 to the 5th. Again, 2 times 2 times 2 times 2 times 2, which becomes 32. 3 to the 3rd is 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. 4 to the 3rd power is 4 times 4 times 4. And 4 times 4 is 16. 16 times 4 is 64. 6 to the 2nd power is 6 squared. So that becomes 36. Here we have a fraction, a half times a half times a half times a half. Again, the top number stays a 1. And 2 times 2 is 4, times 2 is 8, times 2 is 16. And then our last one, 1/3 squared is 1/3 times 1/3, which is 1 to the 9th. Number 3. All right, here's a problem now where we're going to be blending together what we've talked about before by finding some interest, okay, but also thinking about that we're multiplying something repeated times. So it says Claire made $160 babysitting last summer. She put the money in a savings account that pays 3% interest per year. If she doesn't touch the money in her account, she can find the amount she'll have next year by multiplying her current amount by 1.03. Remember that 1.03 means that, what does that mean? You recall? That means she gets 100% of what she has, and she's going to add to it 3%, right, from there. And as you write this as a decimal, that becomes a 1.00. That's 100% plus 0.03 for the 3%. So that's where you end up with a 1.03 as the number she's going to multiply by. Now she's going to multiply it for 1 year, and then it says for 2 years. So for 1 year, that's pretty straightforward, no problem. We do 160 times 1.03. And when you do that with your calculator, or you do it long division by paper pencil, you end up with $164.80. And again, at this point, you're like, okay, that's easy, no problem. And even if they say 2 years, well, remember the key thing here is that if it's 2 years, I would then take this answer and I'd multiply that answer again by 1.03. Now again, you can do that and you'd end up with $169.74. That works. But what we've really done is we've taken the initial value of 160, all right, and we multiplied that value by 1.03, and then we multiplied it again by 1.03. So what we've really done here is we've really said, let's take $160 and let's multiply it by 1.03, however many days it's going to be. So, or years, sorry. So in the first one we did 1 year, but the second one really was 2 years. And you could set it up that way. That's helpful when you look at part B, where it says how much would you have in your account after 5 years. Again, I could continue the process of saying, find out where she started, times 1.03, have a new answer. Find out what she is there, times 1.03, that's year 2. do it again for year 3, do it again for year 4, do it again for year 5. You could certainly do that. Or, because it's repeated multiplication, we could do 160 times 1.03, and we're going to do that for 5 years. All right? So when I do it by 1.03 to the 5th power, that's like saying, okay, I'm going to take my calculator here, and I have 1.03, and I do that 5 times. Okay? And if you're using a fancy calculator, perhaps you could change the exponent there. But for now, I'm going to do 1.03 times 1.03. That's 2. Times 1.03. That's 3. 1.03. That's 4. Times 1.03. That's 5. And so now I'm at this crazy number, 1.159. I don't even know, right? So this becomes a 160 times that, which is 1.15927, blah, blah, blah. Okay? I'm going to multiply that then, the answer, by the 160 where I started, and I end up with $185.48. You could again get that same answer by doing it the 11111 way. I still did 111 way by doing 1.03 5 times. So it's the same thing. Your calculator, there are ways to make that a little faster by substituting the values for exponents, but that's another lesson. C, write an expression for the amount of money Claire would spend after 30 years if she never withdraws money from her account. Okay, so 30 years is going to be what? The initial amount, 160, times the amount she makes each year, 1.03, and that's going to happen 30 times. And that's the idea there. Again, it's repeated multiplication, so we can use an exponent there to solve that. Number 4, the equation y equals 5,280x gives the number of feet, y, in x miles. So this is my feet, and this is my miles for my variables. What does this number represent in relationship? So this number represents what? 5,280 represents the number of feet that are in 1 mile. So that's what that number is for. It tells me how many feet are in actually 1 mile. All right, I'm not writing it down because you got to write your own answer for that one. Number 5, the points 2, 4, and 6, 7 lie on a line. What is the slope of the line? Okay, so for slope, we have our x and our y variables, x and our y, and slope is going to be y, the second y minus the first y, over the second x minus the first x. So when I plug and play here, my second y is 7, my first y is 4, so 7 minus 4, all over second x minus first x. 7 minus 4 is 3, and 6 minus 2 is 4. So my slope is 3 over 4, which is choice D. And finally, number 6, this is a blast from the past from unit 2 here. Here we go. It says the diagrams show a pair of similar figures, one contained in the other. And we can see we have a little triangle right here, right? All inside of the larger triangle right there. Okay, and my big triangle right there. Name a point and a scale factor for a dilation that moves the larger to the small one. So we're going to be going big to little, which means we're going to be decreasing, right? So my scale factor is probably going to need to be some sort of fraction that makes that a smaller item there. So large to small. So that point, the point is the one that won't change. The point has to be in both objects. Okay, and so in our case here, we would say that our point is going to be A, and A is going to be our center of dilation. So everything's going to be centered around that point there. And so as you look at it here, we notice that we're starting at the larger one, right? Large to small, large to small. I'm at, over here to point, I'm at point 3, and the small one becomes over here, goes to 1. When I look at a point like up here at E, I'm at 6 on the y-axis up here, and it's going to drop down to 2. So remember, a scale factor is something that I can multiply by right in here, again and again, in order to change one to the other. So go from the large triangle to smaller triangle. I'm going to multiply a point on the large one by some number to get me to 1. So think about 3 times some number is going to get you to 1. What's that going to be? Well, if I solve for x, I would divide both sides by 3, and so x equals 1/3. So my scale factor is just going to be that. Our scale factor is 1/3. A is my center dilation. My scale factor is 1/3. I can test it out by checking here. If I have 6 times the scale factor of 1/3, what do I end up with? 6/3, which reduces to 2. Matches that, so we are okay. All right, that's it for today. Have a great one. We'll see you next time.